Hi, folks. So it doesn't say on the slide, but I work at Cloudera. This is work I've done on my own recognizance. But if you want to hear about work I've done during the day, I guess, I'm giving a talk immediately after this next door about interpretable machine learning products. But this is an operations talk. How many in the room know what serverless is? OK, most of you. So this is going to be pretty high-level material in that sense, but I think the connection to data science and machine learning may be a new idea for some of you. So these are computers. As we all know, these things are dreadful things. We don't want them. And one of the wonderful things about the cloud is you no longer have to live with your computers. Their feeding and care is somebody else's problem, which is great, but doesn't solve all your problems. So you still have this problem, which is that you now have a very efficient way of setting money on fire. That's partly because of uncertainty in billing, partly because cloud gets expensive fast for modestly complicated applications. And one of the reasons for that is inevitably machines stand idle. They are not necessarily fully utilized at all times. And you've still got a problem, which is the computer is somewhere, and that means you need to configure, secure, and maintain the operating system. This is a recent video of me configuring, securing, and maintaining an operating system. And it's a task that never ends. And it's not necessarily what I want to do for a living. Sometimes it's fun noodling around with kernel modules, but it's not generally what most of us are paid to do. And for most people, it's not what makes their employer money. What makes their employer money is business logic, applications, and machine learning. So we'd love to focus on that. So you can think about moving to the cloud as putting the server in the trash and forgetting about that. That's now somebody else's problem. It's been abstracted away. The conceit, at least, or the goal, or the claim of serverless is that you can put two more things in the trash and forget about them. One is the operating system. The other is the container technology. And all you're left with at that point is the application, the business logic, the model, the machine learning. That's the goal, anyway. And that's the goal of serverless. This is what serverless is in a slide, basically. Serverless is, you can think of in simple terms as computers that exist for the duration of a single function call. So this isn't microservices, computers that serve a single function. It's computers that exist literally for the duration of a single function call. So this is a serverless infrastructure that offers an adding machine. And in between these two calls to the adding machine API, the person who deployed this application has no infrastructure. And the nice thing about that is this. You are charged by the second, essentially by the CPU second, modulo some overhead associated with setting things up. Your pricing scales in exact proportion to how much time you're using these applications for. And generally speaking, for many use cases, that will result in a significant saving. Just as an example, and this is not machine learning or data science, these are the numbers for the readability API. Readability is an API essentially a little bit like Instapaper or reader mode in Safari that takes an article on the web that's full of pull quotes and advertising and images and extracts out the actual legible text. That's available as an API. They used to run it on EC2, where it cost them $10,000 a month. They switched it over to AWS Lambda, one of these instances of serverless, and costs went down to $400 a month, which is lovely. Here's how you deploy on serverless. I'm getting to the data science, I promise. App.py is a Flask server that has one endpoint time that tells you the time. No one's going to win a Turing Award for this, but here's how it looks deployed locally. We run it, and we can curl that localhost URL. And while we're not expecting to win that Turing Award, we would like to share it with the world, so we'd like to deploy it. And we're going to do that using serverless. I usually do that using a tool called Zappa. There are alternatives. Chalice is perhaps the best known one. That's the official AWS client. I like to use Zappa because, in principle at least, it is agnostic about your cloud provider. And Cloudera is all about being agnostic about cloud providers. When I run Zappa in it, it looks at that file app.py, figures out what the endpoints are, and in particular figures out what the dependencies of that application are. When I run deploy, it's bundling all those dependencies up with the application, essentially into a tarball, sending them up to AWS and configuring publicly accessible URL endpoints and various firewall-y stuff that is, for our purposes, bookkeeping, and it's wonderful to have it taken care of. And what you get after some other output that I've truncated is the URL. If you visit that URL, you get the time, and this time is in UT because it's on the Amazon server. What's actually happening when someone visits that URL? Lots of clever things involving containers that AWS engineers understand and I don't. But in general terms, from the point of view of the application developer, here's what's happening. A new machine is created. The code is deployed onto that machine. It receives the input from the HTTP request, computes the result, returns the output, and then crucially, here's the important bit, the machine is destroyed. That has implications for the application and how it can be structured. Principally, there's this. The application cannot have internal state. It cannot remember what happened the last time the function was called without the help of an outside service, such as a database. You could, by all means, do that, but just within serverless, you cannot have state. Nor can these workers, if you like, communicate directly with each other. There are workarounds for all these things, but fundamentally, we're working in quite a functional, pure function world. There's another much more pragmatic engineering limitation that will probably become less true with time, which is that serverless instances are low-powered, short-lived machines. They're low-powered. In the specific case of AWS Lambda, they've only got 1.5 gig of RAM at most, and crucially, the function has to finish in 300 seconds. If it doesn't finish in 300 seconds, tough. The computer shuts down. You don't get half a result, you get no result. That constrains what you can do, but if you're thinking pure functions, low-powered machines, that sounds a little bit like the mappers in MapReduce. You're thinking along the right lines for the rest of the talk. This is a picture of data science, and we would like to do this sort of stuff on serverless for many reasons that I'll articulate in a second. So how can we do that? I just want to really, the focus of this talk is to advertise some work that I was not involved in that I think is wonderful. This is a paper that came out of Rise Lab at Berkeley about fundamentally it's about a new Python tool called PyWren, and that's what I suggest you play with. The paper's really interesting. And you can tell from the title, the goal here is to democratize and make more inexpensive what has traditionally been quite expensive and complicated, namely distributed computing for analytics. PyWren can be seen as an alternative or a lightweight replacement for tools like Spark or Hadoop. How so? Well, PyWren essentially abstracts away serverless as a back-end computational engine for embarrassingly parallel operations. So you've got a very simple code snippet here. We instantiate an executor. This is this object that knows how to, on demand, create Lambda instances. And then any function that we can map across inputs. So this is, the last line here is the thing you might normally write as a list comprehension in Python. If you can turn that into a Python map function, then you can turn it into a PyWren map function. And we're mapping expensive function across list of inputs. And we get the results quickly and inexpensively and with on-demand infrastructure. That's what's going on in the background here. Can I have a couple more minutes because, yeah. So as a specific example, you can imagine scraping a website for lots of URLs. That's something I do day to day. Perhaps a more interesting and classical Hadoopy benchmark is this. It's counting the words in a document. Docs there is a long list of documents, complete works of Shakespeare, Wikipedia, whatever. We've got a Lambda function in there, Lambda, the anonymous function, not Lambda, the AWS thing, that knows how to count words. And then we collate the results. And all the computation is happening in the cloud. Just as a rough idea, all benchmarks are dubious at best, but this is the benchmark reported by the PyWren folks. Ballpark, a few hundred AWS Lambda instances, roughly equivalent to a 100-node Spark cluster for that kind of classical, embarrassingly parallelizable analytics distribution. But that's not the point. The point is I was able to do that on my own without calling an adult, without calling a data engineer to help me get set up, without speaking to the people who hold the purse strings and are able to make decisions like we want to stand up a long-lived Spark cluster. Machine learning, of course, not all of it is embarrassingly parallelizable, but some of it is. I think the most obvious example is hyperparameter search. That's, of course, when you essentially try lots of numbers and see which ones are the best. That is embarrassingly parallelizable. As long as training, you can do it in under 300 seconds, you can use PyWren as the executor for that kind of job. It also raises the interesting possibility of mapping gradient descent across these things. Not all implementations of gradient descent are trivially, embarrassingly parallel, and there are, of course, communication costs to sending large batches of data out to nodes. So this isn't as simple as mapping a URL scraper across a PyWren executor. Additionally, in the real world, distributed systems involve stragglers, they involve faults, and you need a distributed gradient descent algorithm that is robust against that, let's say, asynchronicity. I'm working on this right now. If anyone else is working on this, I'd love to talk to them using serverless as the back end for those kinds of fundamental machine learning calculations. Finally, PyWren is, I think, a proof of concept rather than something you necessarily want to use in production. There are no managers, there are no guarantees. And in a distributed system, given enough nodes, one of them is going to fail. PyWren won't help you there, unfortunately. So it's up to you to do the kind of bookkeeping that's necessary for that. So this is not a Spark alternative. I'm not saying you don't need Spark anymore. But this is a lightweight, fun thing to play with that I think is very useful for machine learning people and data scientists to be aware of. And that's because, final slide, it raises the possibility of the exciting future where the data engineer and the data scientist are friends again because they no longer have to argue about contention on an expensive distributed system. Thank you very much.